Hello everyone, I hope you are doing well. So in today's video, I'm actually going to go through the 2017 physics multiple choice questions, for the 2017 year. So let's get ready. So question 1. A group of students is considering how to create a magnetic monopole. So, okay, which of the following is correct? So what is a monopole actually? So it has only one pole. That's what a monopole is. So imagine like normally you would have, basically, if I just make this big, okay. Basically, normally you'll have north and a south. Let's say you had a bar. So normally it has north and a south. And monopole is just like, we want only north. Like just one pole. Is that true? I don't think you can make that. But let's just look at the answers. Which of the following is correct? Break a bar magnet in half. So if you break a bar magnet in half, for example, you break it in half, what's going to happen? Well, pretty much it will just create its own north and south again. Like it doesn't actually create a magnetic monopole. Like if you break this in half, it just again creates a north and south. So absolutely not. Pass a current through a long solenoid. Okay, if you pass a current through a long solenoid, it will create a north and a south pole straight away. Nope. Pass a current through a circular loop of wire. Absolutely not. That will again create a north and a south. It is not known how to create a magnetic monopole. D is your answer. It can only be your answer, yeah. Millikan, a famous scientist, measured the size of an electron charge by balancing an upward electrical force with a gravitational force on a small oil drop. So in a repeat of this experiment, an oil drop with a charge of this was placed in an electrical field of 10 to the power 4 volts per meter. Which of the following is closest to the electrical force of the oil drop? Okay, so I'm just going to have a look at my formula sheet. So the formula that's the best to use for this is, alright. Okay, so we've got force equals QE, the charge times the electrical field. Well, because we want to calculate the force, the charge for this case is 9.6 times 10 to the negative 9. And the electrical field is times 10 to the power of 4. So doing this, you should get, 9.6 times 10 to the negative 9 times 10 to the power of 4. You get 9.6 times 10. So it should be 1, 2, 3, 4, 5. Negative, oops, what am I doing? Alright, wait. 1.6 times 10 to the negative 9. Alright, so I think times 1 times 10 to the negative to the power 4. Okay. Oops. Wait. It's negative 19. Sorry. Okay, this is supposed to be negative 19. Yeah, negative 19 times the electrical field. Let's try that now. So 19. Okay, we get 9.6 times 10 to the negative 15. B is your answer for that one. Okay. Two large charge plates with equal and opposite charges are placed close together as shown in the diagram below. So a distance of 5 millimeters. So the distance 5 millimeters. So 5 times 10 to the negative 3 meters. Okay, the electrical field between the plates is 1000. So which of the following is closest to the voltage difference between the plates? So, okay, this is the formula. So we know voltage is equal to ED. Okay, so what is our electrical field? It's 1000. What's our distance? Well, it's 5 times 10 to the negative 3. So multiplying these together, we get 5 volts. A is your answer. A student doing a VCE physics practical investigation uses a step-down transformer with 240 to 200, so it makes it to 12 volts RMS AC. So we have a transformer, and it was initially 240 volts, and it's RMS, and it transforms it to 12 volts RMS. Okay, and it's AC, so that's good because transformers only work in AC current. AC. Okay, Which of the following best gives the ratio of the turns n primary and n secondary? So the number, okay. Well, we know that your n primary over your n secondary is actually equal to your to your voltage primary over your voltage secondary. So, okay, what does that mean? Well, if this is your NP, and this one over here is your NS, because this is your secondary, like, yep, it's pretty much the same. Okay, so this is how the best explanation to do this. Well, imagine, okay, so this is your primary voltage. Like, it starts off this one over here. So this is your VP, your voltage primary. And then it transforms it, steps down it to your voltage secondary. Okay. And we know this ratio, it tells us. So, because they're equal, if we say MP is actually equal to NS, so what's VP in this term? Well, it's 240 over VS, which is 12. So the ratio is 20:1. And here it's saying the first one's M primary, which is in this case 20. And your secondary is 1. So 20:1, that's your ratio. So it should be D as your answer. Yep. Looks right. Perfect. I'll rub that out. Okay. Move on to the next question. A transformer delivers 48 watts RMS to a resistor. Assume that the transformer is ideal. Okay, so what ideal means is that there's no power loss. Which of the following best gives the peak current, current in the secondary coil? So, okay, it's still the same question because it's question 4 or 5. Okay, we know that this was 12 volts RMS and this is 240 volts RMS. And pretty much over here, we're going to use because it's in our secondary coil, this is our voltage, 12 volts RMS. So we know our voltage is 12 volts, 12. So your voltage is 12. We also know that our power is 48 in both sides. So it'll be 12 over here, it'll be 48 over here and 48 over here because it's ideal. There is no power loss. Okay, so we know our voltage and our power, and we want to find the current. So to do that, we know that power is equal to VI. And we know our voltage, in this case, is 12. We don't know our current, and our power is 48. So I is equal to 4. Remember, it is RMS, your actual current, so amps RMS. But here we're talking about peak current. So to get the peak current, it's pretty much multiplying it by root 2. So what's 4 root 2? So doing that, it should be approximately, so 4 times root 2, it gives you 5.6. 5.65, which is approximately C as your answer. Yeah, I feel like a lot of students would get confused here because they would do all these nice, easy calculations, but they will forget to do the last point, which is, remember, this is RMS. It's not actual. We want peak current. So, yeah. The graph below shows the change in magnetic flux through a coil of wire as a function of time. Which of the following graphs best represents the induced EMF across the coil of wire as a function of time? A very typical question. So, how do you do this? Well, pretty much we know that if you remember that EMF is equal to negative N change in flux over time. Think of this as a gradient. Like, think of it as a gradient, like a gradient formula. So, E is our function. N is just a constant. So, just forget about N and just say, remember that negative is an important thing. So, let's keep that negative in there. And your flux over change in time. Okay, so now we have this nice equation. Pretty much, it's trying to find the gradient. So, for example, let's say from here to here, let's try to find the gradient. Let's say we find the gradient and it's like, because it's going up, remember it's positive, so you can see it's going up. So, let's say it's 2. Let's say it's 2. The gradient is 2. But remember, there is a negative, so we just have to put a negative 2 in there. So it's a negative 2 gradient. So if we were drawing the EMF, it will look like this. There will be a negative 2 straight line to that over there. So from here to here. Perfect. And what about over here? Let's continue. Now it's going down. It's going down. Yep. Let's say it's still 2. It's still going down by 2, and now it's negative 2 due to the fact that it's like a downwards negative. So they're a negative gradient. But remember, because there's another negative, we put as a positive. So it becomes positive 2. So this will go from here to here as positive. There we go. Perfect. And yeah, this here, we just put a straight line because it's 0. It's like nothing, pretty much. It's not even 0. It's just like it's an undefined. Yeah. Perfect. So it would look like the green graph. So let's look at A. Absolutely not A. So it's the same graph. Nope. B. Nope. It's just a reflection along the t-axis. C. Absolutely not. I don't know where they got that. And D. D looks perfect. So choose D as your answer. Let's look at this. So the following information to answer 7 to 9. Okay. A model car of mass 2 kilograms is propelled from rest. So rest means that U is equal to 0. By a rocket motor that applies a constant horizontal force of 4 newtons. Okay, as shown below, assume that friction is negligible. So there's no friction. Okay, so because it's going, let's say, to the right, there's a force, a constant force of 4 newtons. Okay. Which of the following best gives the magnitude of the acceleration of the model car? Very nice. Okay. We know the formula F net is equal to ma, Newton's second law, where the force net is the sum of all forces. Well, here, what is the sum of forces? Well, it's only 4 newtons because there's no friction. Normally, there would be friction and let's say some F value and this minus this. But luckily, there's no friction, so it makes our calculations much easier. It's just 4 newtons, so you put 4 here. What's the mass of the car? 2. And therefore, our acceleration is 2 meters per second. It's weird. So that will be C as your answer. Which of the following best gives the magnitude of the impulse given to the car by the rocket motor in the first 5 seconds? Okay, there's actually 2 ways I would do this question. There is this basic formula, impulse is equal to Ft, this formula, and pretty much your force over here, because it's constant, it's just 4, and we multiply it by the time. Well, our time here is 5 seconds, which is 20. That's your impulse, newtons per second, which would be C as your answer. But there's another way to do it. If I was in an exam and I didn't have that formula, I would just use the SUVAT formulas, for example. I know impulse is the change of momentum. So your impulse is mv minus u. Well, u in this case is 0 because it starts at rest. So we can just forget about that. So it's just mv. What's m times v? Okay, that's your impulse. We know our mass is 2, but what about our final velocity? Okay, well, we know our u is 0. We also know time is 5 seconds. And we know our acceleration, in this case, is still 2. And what we're trying to calculate is the final velocity. So here, we would use v equals u plus at. So v, well, 0 is our u. It's just 2 times 5, so it's 10. Your final velocity is 10 meters per second. So now, because our impulse is what? Our mass, which is 2, times your final velocity, which is 10, which gives you 20 newtons per second. So both ways give you the same answer. So yeah. Question 9. With the same rocket motor, the car accelerates from rest, so from u equals 0, for 10 seconds, so t equals 10. Which of the following gives the final speed, so our final velocity? Okay. Because it uses the same rocket motor, so we're still applying that 4 Newton force, our acceleration will be the same. Yep, so our acceleration would be still 2. Now, Okay, what formula? Well, we use V equals U plus AT. Our V in this case is, so what's your U? 0. So 10 times 2, 20 meters per second. So it's C as your answer. Okay, question 10. A student sits inside a windowless box that has been placed on a smooth riding train carriage. He conducts a series of motion experiments to investigate frames of reference. Which of the following observation is correct? Okay. The result when the train accelerates, okay, so we have some acceleration. So let's say it's like A equals 2. That's our acceleration. Are identical to the results when the train's at rest. No. When you're at rest, your acceleration is 0. There is no change in velocity that's happening. So they are not identical. Is A equals 2 and A equals 0 identical? Absolutely not. So A is wrong. The results when the train accelerates, so let's say A equals 2 here, differ from, so they're different from when the train is uniform motion in a straight line. When a train goes through uniform motion, our acceleration becomes 0. And yeah, because it's in uniform motion, well, they are different, so B is likely to be right. Let's look at the next ones. The results when the train's at rest, so at rest is what? Acceleration is 0. Differ from the results when the train is at uniform motion. No, it's A equals 0 still. They are the same, but here it's saying differ, so C is wrong also. And the results when the train accelerates, so we have some acceleration, let's say 2, are identical to the results when the train's at uniform. When the train's at uniform, it's 0, so they are not identical. So yeah, B can only be your answer for this one. Very nice. On average, the sun emits 3.8 times 10 to the negative 10 times the power of 26 joules of energy each second in the form of electromagnetic radiation, which originates from the nuclear fusion reactions taking place in the sun's core. The corresponding loss in the sun's mass each second would be closest to what? Okay, well, we know that the formula E equals mc squared. And it's the relationship between energy and mass. And here we're trying to calculate the mass of the sun each second. So, well, the energy here is 3.8 times 10 to the power of 26 equals m, which is what we want to find. And our c is a constant. It is 3.0 times 10 to the power of 8 squared. So our m value here, if I do on my calculator, 3.8 times to the power of 26 over 3.0 times 10 to the power of 8 squared. That gives me 4.2 blah, 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 something around there. It's a very big number. So B can only be your answer for this one. Yeah. So just look at the relationship. Like if I'm doing this question, to be honest, if I just see energy given to me and they're trying to make me do like calculate the mass, or in any given case, they just give you the mass and they like calculate the loss, or in anything like that, I would look at EMC squared, like, this formula. Because it gives you the relationship between energy and mass. So, yeah, that's how you do this question. All right, they use the following information to answer question 12 and 13. A model car is on a track and moves to the right. It collides with it compresses a string that is considered as ideal, as shown in the diagram below. The car compresses the spring to 0.5 meters. Okay. The car comes to rest. The force distance graph for the spring is also shown. Assume that the friction is negligible. Okay, so what's going to happen is here, let's say its kinetic energy is at its maximum. Imagine the car's going so quick, and when it hits the spring, it starts slowing down. And let's say it hits here, this point, which is 0.5 meters. Over here is when the car actually stops. Like it has that time where its velocity becomes 0. What does that mean? Well, it means our kinetic energy is 0 because our velocity is 0. What happened to all that energy? Well, all that energy is going to pretty much be converted to elastic energy, like elastic spring energy. Because this elastic would be like this. It would be very thin now because it's been stretched. So yeah, with knowing that, what does that mean? So let's have a look here. Let's look at the question. Based on the graph above, what is the best estimate of the spring constant? Very nice and easy question. Well, the spring constant for a force and a position graph is its gradient. So let's just have a look at the gradient. Let's pick 2 points. I'll pick this point over here and I'll pick this point. So the gradient for this is 400 minus 0 over 1 minus 0, which is 400 newtons per meter. So only C is your answer. Very nice. What is the initial kinetic energy of the car? Initial, this is important. Remember, it starts initially with a maximum kinetic energy over here. So because we know it gets compressed, let's say at 0.5, and all that kinetic energy now is at spring, we can pretty much look at this graph and calculate the energy. Well, because at 0.5, which is over here, if we calculate the area under this graph, it will give us the kinetic energy, your initial kinetic energy. Let's do that. So this is what I want, this over here. So the area is half. Okay, 0.5, which is another half, times 200. So 200 times half is 100, and times another half is 50. So B is your answer for that one. Not too bad. Question 14. A teacher stands in the corridor at a short distance from the open door of her classroom, as shown in the diagram below. She can hear her students, but cannot see them. Which of the following best explains why the teacher can hear her students? Okay, this is due to diffraction. You can see the door is like a slit. And okay. Let's look at the answers. So the speed of sound is much greater than the speed of light. Absolutely, that's rubbish. The speed of light is much higher and greater than the speed of sound. And in this case, it's not even useful to know that for this diffraction. Like diffraction does not depend on those factors. So A is wrong. The speed is sound is comparable with the speed of light. No way, they are not. Yeah, absolutely. Remember, the speed of sound is like 365 meters per second, whereas the speed of sound is 3.0 times 10 to the power of 6. It's much greater the speed of light. So yeah, that's wrong too. Sound diffracts because the wavelength of sound is much smaller than the width of the door. Now you should know this formula here. Like, what is diffraction? Well, diffraction is pretty much equal to your wavelength over your width. This is what it is. If this ratio is, let's say, equal or greater than 1, diffraction is it pretty much exists. Diffraction exists. But when it's less than 0, like for here, when it's less than 1, diffraction is negligible. Like you can't even, diffraction becomes quite useless for that. So using this kind of ratio, let's look at the question. It says, sound diffracts because the wavelength of sound, so this wavelength over here, is much smaller than the width of the door, the width. Okay, this is actually rubbish because let's say we're saying if the width is smaller. No, we're saying that the wavelength is smaller. If the wavelength is smaller, it means our diffraction, this here over here, becomes smaller. So this ratio over here becomes less than 1, which means that diffraction is not occurring. So absolutely nope. C is not your answer. So it means only D is your answer, to be honest. Let's just double check D too. So D says sound diffracts because the wavelength of sound, so your wavelength of sound, is comparable with the width, so they are equal. If they are equal, well, it is equal to 1. And remember, if it's greater or equal to 1, sound diffraction is actually pretty much it exists. So absolutely D is your answer for that one. Okay. Lee listens while a police car is with a loud siren comes towards her, travels past her and then continues on the way from her. Compared with the sound she would hear from the siren if a police car were stationary, the sound has. Okay. So this is Doppler's effect over here. I know for a fact. But here it says, Lee listens with a police car with a loud siren coming towards her, traveling past her and then continuing on her way out, away from her. Compared with the sound she would hear from siren if the police car was stationary, the sound... Okay, so if the police car was stationary, the frequency is constant. Like, it's, let's say it was next to her and it's like the same sound. The frequency is the same. But here it's saying, okay, the sound... let's look at A. A higher frequency as a car comes towards her. Yes, absolutely, that's true. So imagine a car coming towards you. You would hear, of course, a higher frequency coming towards you. And a lower frequency when the car moves away. Yes, when the car starts moving away, you start to hear less and less of the sound. So the frequency becomes smaller. A could be right. Let's just put like a tick on it. Let's look at the next question. B, a lower frequency as a car is towards you. Nope, so that's wrong straight away. A lower intensity. No, intensity. Look, when you look at a Doppler's effect, it's all about frequency. We're dealing with frequency using Doppler's effect. So don't even think of intensity. When they use the word intensity, it's always wrong. The same frequency at all times. Nope. So only A is your answer for that one. Very nice and easy. A diffraction pattern is produced by a stream of electrons passing through a narrow slit, as shown in the diagram below. Okay, we can see this narrow slit over here. This electron diffraction pattern can be used to illustrate Heisenberg's uncertainty principle. This is because knowing the uncertainty in the... Okay, this is nice. I love Heisenberg's uncertainty question. They're very basic if you really understand them. Okay, well, let's look at what is Heisenberg's uncertainty. This is the formula that you should always have. So, it is, for example, change of P of x is a change of x is equal to h over 4 pi. So this h over 4 pi is a constant. So don't even think of it too much. Just think of it as like a constant, like a number. Let's say it's 2. Just think of it as a constant. And this is, just have a look at this. So this is your momentum in the x direction, and this is the width, like the position. So let's just have a look at one. Let's look at the answers and see if we can see which one's right. So electron speed is large, leads to uncertainty in its kinetic energy. Oh, hell no. What the hell is this? This is not Heisenberg's uncertainty. It pretty much, yeah, when it says speed or kinetic energy, it's, yeah, don't bother with that. Slit width is small. So the slit width is small, leads to a large uncertainty in the electron's momentum in the y direction. Okay, so the slit width, so this width over here, is small, which would lead to a large uncertainty in the electron's momentum in the y direction. Okay, makes sense. So we know we are certain that it's going to be in the x direction, because just imagine this arrow, we know this arrow is going right inside of it. So we know it's certain it's going to the x direction. But what about the y direction? Well, that's where uncertainty happens. If the width is small, there is more uncertainty if it passes through the y direction. So it says slit width is small, leads to a large uncertainty in the electron's momentum in the y direction. B looks very correct. And let's just look at this over here. Let's look at the principle, the formula. Changing py, changing y is equal. Let's say it was equal to 2. That's like a number, a constant. So because the slit width is small, so this change in y becomes small. What happens? Well, our change in momentum becomes large. It has to become large so it can become 2. Let's imagine, like, if change of y becomes small, it means this number 2 would become, let's say, smaller. But remember, it is a constant. So what for compensating this change in p, your momentum must be greater. So yeah, so here slit width is small, leads to a large uncertainty in electrons' momentum in the y direction. Yes, it does. So B is absolutely right. C says electron's momentum in the y direction is small. So if the electron's momentum in the y direction is small, it leads to a large uncertainty in its slit width. Pretty much what's happening is they've kind of made this opposite of answer B, but that's wrong. So yeah, this is not good also. Electron's angle of approach to the slit leads to a large uncertainty in the electron's momentum in the y direction. Yeah, don't worry about D. D is just trying to trick you. This is not for your study design. Just, yeah, that's how you should just look at the basics of Heisenberg's uncertainty. Yeah, so B is your only answer for that one. Quantized energy levels within an atom can be explained by... Okay, what is quantized? So quantized means... This is how I know what quantized is. Quantized is certain, like, energy values or wavelengths you need to... are needed for, like, let's say an electron. Certain energies or wavelengths are needed for certain electrons to pretty much become quantized or get from a high energy state to a lower energy state. Yeah, so let's just look at the answers here. Electrons behaving as individual particles with varying energies. No, that's absolutely wrong. Atoms having specific energy requirements that can only be satisfied by electrons. Atoms having specific energy requirements, yes, that can only be satisfied by electrons. No, B is wrong. Electrons behaving as waves, okay, true, with each energy level representing a diffraction pattern. Not true, that's wrong, diffraction pattern. Let's look at D. Electrons behaving as waves, that's also true, with only standing waves, yes, at a particular wavelength allowed. Yes, absolutely, that's what quantized means. Only things, certain wavelengths or energies are allowed for a standing wave to occur. So absolutely, that is, D must be your answer for that one. All right, is that right? Electrons behaving as waves with only standing waves at a particular wavelength allowed. Okay, perfect. Question 18. Two students, Rob and Jane, measured the current in the same circle on separate occasions. Rob obtains the following reading. Okay, he gets this, and this is his average. And Jane obtains the following reading, and this is her average. Okay, so the true value of the current is known to be 9.35 milliamps, whichever following best describes these two set of values. Okay, because this is the true value, and we can see that Rob gets the average is the same, it would mean that he's more accurate. He's more accurate in his answer. And remember, accuracy is how close your answer is to pretty much your, like, it's how close your mean value is to the real value. And yes, he's very close. He's got the same value. So yeah, it means his one's more accurate, whereas her one is less accurate. Jane's one's less accurate. What about precision? Well, in this term, like, precision is the range of values. For example, if we look at Rob, we can see that his precision's less because his values, like his range of values, is much, it's not closer to the 9.3. Like if you look over here, 9.21, 9.10, 9.6, very large. Whereas if you look at Jane's one, she got 9.2, okay, 9.25, so she's getting closer to that 9.35, 9.31, and 9.36. So she's very close to that 9.35. So normally we would say Jane has a higher precision than Rob. So knowing these, let's look at the questions. Which of the following best describes the two set of measurements? Rob's results are more accurate than Jane's result. That's true. Okay, that's absolutely true. Both sets of results are equally accurate. Nope. Rob's results are more precise than Jane's. No, Jane's one's more precise than Rob's. Both sets of results are equally precise. Nope, so A can only be answer. Question 19. Which of the following best describes a hypothesis? It is a possible explanation that needs to be regularly tested by experimental evidence. Yes, it's true. An explanation that has been supported by rigorous experimental evidence. No, when we make a hypothesis, we're trying to make a general assumption. We're like, if it, by like knowing theory, if we, let's say, put this, I guess, like you're assuming, I guess that this will happen. So it's not pretty much, yeah, it's not explanation that has been supported by rigorous experimental evidence. It wouldn't be that. A statement that is widely accepted by scientists, that is a theory, not a hypothesis. An explanation that is mathematically correct. No, a hypothesis is something that you test to see if it's wrong or correct. So yeah. So only A is the best one here because it's a possible explanation that needs to be rigorously tested by experimental evidence. True. You need to test it if it works or if it doesn't. If it doesn't, yeah, your hypothesis is then wrong. Question 20. Which of the following statements about systematic and random errors is correct? Remember, random errors are things that, I don't know, you can think of it as things that are just coming random, like random errors, yeah, they're like random errors that happen. Whereas systematic errors, just remember, systematic errors is something wrong with the calibration of a machine. For example, if you're measuring mass, and let's say this mass is it's wrong by some values. Let's say it's wrong by like, I don't know, 2 grams. It means all your values are going to be wrong by 2 grams. So yeah, so this is what we call a systematic error because all your values, your set of values are going to be wrong by 2 grams. And whereas random error, one will have 1 gram, one will have 2 grams, one will have 3. So it's very randomated. So yeah. All right, so that's what they mean. So random errors can be reduced by repeating an experiment. Absolutely, yes. Random errors, if you repeat an experiment, your average value, your mean value becomes closer to the real value. So that's true. Both random and systematic errors can be reduced by repeated. No, systematic errors cannot be reduced by repeating readings. Remember, systematic is it's something wrong with the calibration of the machine. So absolutely, B is wrong. Systematic errors can be reduced by repeated readings. Nope. Neither systematic nor random errors can be reduced. Also, D is wrong. So A is your answer for that one. Yeah, I hope you guys enjoyed this video. If you have any question, please make sure to like and subscribe to this channel. Yeah, if you have questions, please put them down in the description. I'll try to answer them. And I hope you guys enjoyed this video. This was a lot of my students have been telling me to do this exam. Just a quick walkthrough through it. I hope you guys enjoyed this video and learned something. And please make sure to share and subscribe to your peers. And yeah, I hope you guys enjoyed this video. Take care of yourselves. Have a good day. Bye-bye.